Okay, so okay, so this way it will come, and during the negative half cycle, the thyristor will be off, but the freewheeling diode will be on, and the load, that is RL load, will discharge its storing charge through the diode. So what will happen? The current, the output current will be
Hello.
observed. Hello.
Hello. Sorry, ma'am. I could not connected earlier because in my home there is no network. That's why I have to step out my home. I'm attending on road class. That's why I'm
Okay. ওকে ওকে দেখি এটা রেকর্ড হচ্ছে। ওকে, all of you please mute yourself so that okay. So let us start. So during so this is the controlled rectifier with RL load and freewheeling diode. As we have already seen that the without freewheeling diode, what was there, the current conduction is not continuous. It is in the previous case we have seen that from beta to 2 pi plus beta it is off. Okay, so if I want the continuous conduction of current, then we will have to use the freewheeling diode. During if I use freewheeling diode during positive half cycle, the thyristor is on in and it will start charging the inductance, which is the charge storing device. It will start charging, and during the negative half cycle it will discharge its charge, so we will get the continuous conduction of current. During the positive half cycle, the conduction of current we will get because of the conduction through thyristor, and during negative half cycle the conduction we will get due to discharging of charge storing device, that is inductance, through the freewheeling diode. So we will get the continuous conduction of current. So you can see in this picture of waveform that the voltage started at, this is actually the thyristor voltage, okay, alpha, and it ends at pi. After that, no conduction output voltage is not available. Okay, so from pi to alpha, 2 pi plus alpha, we will not get any voltage output, but current is flowing from alpha to pi, and then again pi to 2 pi plus alpha. So again from 2 pi plus alpha it will again come into conduction. So continuous conduction can be available due to this freewheeling diode. This is actually the facility or the advantage of freewheeling diode over this normal diode. Okay, so here also the output voltage we can get average output voltage 1 by 2 pi integration from alpha to pi. As I have mentioned that here the though we are getting continuous conduction, we will consider only the current conduction of thyristor only. Okay, so freewheeling diode conduction we will not consider. So here from alpha to pi, Vm sin omega t d omega t, and from integrating this with the limit alpha to pi, it will be v by 2 pi 1 plus cos alpha. Okay, so again in this equation, if you put alpha equal to 0, you will get uncontrolled diode conduction with RLO with freewheeling diode. Okay, so this way the thing is thyristor, we are getting the thyristor equations, and thyristor is only useful as we are getting controlled conduction of the current through the device. So if you want uncontrolled one, if you put alpha equal to 0, then you will get the equation, same equation as the uncontrolled device. Okay, So this is our freewheeling diode. Next, we'll discuss about the RE load. As we have already discussed with the uncontrolled rectifier, where diode was used with load R and the battery E. Here E is the battery. Okay. So in this figure you can see the supply voltage is given with thyristor and the load R and E connected in series. So at in this case the picture you have to see the waveform. You can see this is the signal. This is the sinusoidal source voltage Vs, and at alpha again the thyristor is triggered at alpha, and the battery voltage is E. This one, this is the E voltage, and so the output voltage you can get E. So at t equal to 0 you will get E. At alpha you will get the voltage. This is the alpha. When it is being triggered, it you will get the source voltage. Okay. So here this is the point. This point is alpha. Okay. This point is alpha. This is actually, this point is theta, and theta is the point where the source voltage and battery is equal. So at theta, SCR is in forward blocking mode. After this, once a trigger pulse is given, SCR will work as normal diode. So at omega t equal to theta, source voltage is equal to the battery voltage, and that is equal to Vm sin omega t. So from that we can get theta equal to sine inverse E by Vm. Since Vs equal to Vm sin omega t, sin omega t will be equal to E by Vm. So theta will be equal to, since omega t equal to theta, so theta will be omega t equal to sine inverse of E by Vm. So that omega t is equal to theta, so theta equal to sine inverse E by Vm. Okay. So the output current peak is at omega t equal to pi by 2. This is the output current. At pi by 2 we will get the maximum output current. Okay. So I O, or the I output volt current, will be equal to Vs, the supply voltage, minus E, the battery voltage, divided by R. This will be the output current. Okay. Now supply voltage will be equal to the output voltage, so this can easily equal to can be written as V output minus E by R. So output current will be equal to 1 by 2 pi integration alpha to pi minus theta, alpha to pi minus theta, that is from that the conduction started. Vm sin omega t, that is this one Vs, instead of Vs we will get Vm sin omega t minus E by R d omega t. So take the common and we'll get 1 by 2 pi R Vm and sine omega t. Sine omega t, it will be cos omega t minus cos omega t, limit alpha to pi minus theta minus e d omega t, and d omega t, the limit is given pi minus theta minus alpha. So from that we will get 1 by 2 pi r Vm cos theta plus cos alpha minus pi minus theta minus alpha. So to convert it to uncontrolled rectifier, you have to put what? Alpha equal to theta. In controlled rectifier for any RE or RLE load, alpha equal to theta. So in this case, you may get some even harmonics along with DC components. Okay. Now we will discuss how to remove the even harmonics and why it is required to remove the even harmonics. Okay. So even harmonics are basically difficult to remove. In this case, we may get some even harmonics with all our signals. So actually for this case, even harmonics removal is difficult. For that we have to use full wave converter. These are all the half wave converter. Why half wave converter? Because we are using only single diode or single thyristor. So it is half wave rectifier, and for removing the even harmonics we will have to use full wave converter. uh, with this there will be there we will be able to introduce some negative half cycles also. Then the waveform will be sinusoidal. Sine wave will have odd harmonics. With that we will be able to eliminate the DC component and even harmonics. And if I get both the cycles, that is positive half cycle and negative half cycle, if I want to evaluate the average voltage, then the average voltage will be zero, because when we get the both the cycle, the average output voltage will be equal to zero. If we apply DC to a transformer, what will happen? If we apply DC to a transformer, the frequency will be zero, since flux is proportional to inversely proportional to frequency, and flux will be too high and core gets saturated and winding will be burnt. These are the difficulties when we will get the DC components or even harmonics. Okay, so we are having full wave converter. So one example of application where we can use half wave rectifier is pulse generator. Okay, so there the input is DC and high frequency low power devices. So conventional transformer made of soft iron. It is always used for low frequency high power application. In case of power electronics, high power application is used. So we with that power using DC component only transformer, with the only you with that high power using only DC component, the transformer will be burnt. So at source side, DC component and even harmonics should be zero. So we have to remove the even harmonics, and for that we will use the full wave rectifier or full wave converter. Okay, so because when the transformer case, the output voltage is 4.44 into flux into frequency into the into t, the time. So here, if flux increases, since the flux is inversely proportional to frequency, it will get saturated. Flux will get saturated and the transformer will be burnt. So DC component and even harmonics of the signal should be removed. So we will use the full wave converter, controlled converter, single phase, full wave, controlled rectifiers. Okay. So up to this, anybody has any question?